Hi everyone, my name is Sarah Scott and I am a PhD candidate at Duke University in Civil and Environmental Engineering, and I'm also an intern at the NASA Langley Research Center where I support the efforts at the Atmospheric Science Data Center, and I'm presenting on handling missing data through temporal forecasting and spatial embedding of high-resolution TEMPO observations. So TEMPO is NASA's newest Earth-observing satellite as a North American constituent of the Air Quality Constellation in efforts with South Korea's GEMS and the ESA's Sentinel-4. These geostationary instruments are UV visible light spectrometers measuring trace gases in the atmosphere. While Tempo's geostationary orbit enables hourly daytime retrievals on a neighborhood scale across North America, its reliance on solar illumination restricts monitoring to daylight hours only, introducing nighttime gaps that limit emission tracking. And these nighttime gaps are compounded with another common source of missing data, which are clouds, where clouds cover about 45% of scenes through all of Tempo's field of regard. So for the nighttime forecasting, we utilize Meritu-based meteorology variables through NASA's Power API, as well as US EPA air nav sensors that provide ground-based air quality measurements. And most importantly, to aid in predictions, we have support from the Pandonia Global Network with their Pandora stations. And in this implementation for nighttime forecasting, we use their direct lunar scans to provide tropospheric column support at night when the tempo instrument is inherently offline. With these lunar measurements, we're able to expand our coverage when the sensors are exposed to illumination from the moon, which, does vary throughout the month depending on the phase of the moon and if the moon is above the horizon in order to cast on the Pandora sensor. To perform these nighttime predictions, we utilize popular and classical machine learning techniques such as random forests, which are known for being outlier resistant due to their ensemble-based non-parametric definition. And we also utilize Gaussian processes, which are powerful probabilistic regressors where their kernel definitions aim to capture temporal, spatial, and seasonal trends. So provided the input parameters previously listed, we predict over a joint missing data task to get predictions at night, as well as during one of Tempo's special operation missions, where the satellite performed high frequency scans over the wildfire event in January 2025, which was over California in the United States. This time series of predictions reveals comparative performance results between random forests and Gaussian processes overnight and during the special operations, where the Gaussian process seems to average out and better utilize lunar Pandora data as opposed to the overestimation that comes from the random forest predictor. And we also used a linear regression model as a baseline for comparison. Moving to our pixel gap filling technique, we apply a 2D partial convolutional unit that passes the normalized tempo raster image with its binary mask and feeds it through a 5-layer unit that has additional support in the network's bottleneck. The work done for this task is publicly available on the ASDC's GitHub, accessible through this QR code, where provided user-defined areas of interest and user-defined time periods of interest, we provide a tutorial demonstrating pixel gap filling on obscured tempo data. Because this is an unsupervised task where we don't have ground truth pixel information to train the model on beneath the clouds, we once again utilize Pandora ground stations, using them as a ground-based reference to ensure the reconstruction pixels align well with real-world measurements when and where the Pandora data are available, which does vary every hour. Our network was able to capture and learn semantic pixel level information associated with urban emission hotspots and generated spatially consistent and realistic outputs, despite the absence of true ground truth pixel data for explicit validation. And our future work will focus on advancing our current 2D partial convolutional model for a 3D spatio-temporal interpolation for intra-hourly tempo predictions. We aim to leverage computer vision techniques to generate finer scale temporal estimates between each hourly tempo scan, capturing more continuous and dynamic patterns in atmospheric behavior. And so, yeah, with that, thank you for watching, and a special thank you to my advisor, Hazem Mahmoud, for all his help with the work presented here. I can be reached with any questions at the email address presented here, and the tutorial presented, as well as other tutorial work utilizing machine learning for tempo data, can be found at the QR code here.